Hi, everybody. So then in this video, I'll be going over an application involving linear algebra and specifically linear systems called balancing chemical equations. So when you balance a chemical equation, it's just some kind of algebraic equation that gives the relative number of reactants and products in the reaction and has the same number of atoms of each type on the left and right hand sides. The equation is written so that the reactants are usually on the left and the products are on the right with an arrow in between to show the direction of that reaction. I'll give you an example of an unbalanced equation below. I want to know then, for the reactants and products, how many molecules of each do I need in order to guarantee the same number of elements on each side of that equation? So let's suppose then that x1, x2, x3, and x4 are just the number of molecules that you see present in the chemical equation. And I'll write it so that the chemical equation should be balanced once I assign, in this case, integers to these different values. Now, if you consider only the element C, which is carbon, and count the number of carbon atoms on the left-hand side and carbon atoms on the right-hand side, you see that on the left, you'd have 7 times C1, and on the right, you'd have just 1 times C4, 1 times X4. That equation then gives you the representation of guaranteeing that we have the same amount of carbon atoms on each side, depending upon the number of molecules we have of these particular reactants and products. You can do the same thing for oxygen. If you just look at the equation, you'll notice that for every molecule of C7H68O2, you get 2 oxygen. So then since there's X1 of them, if I take 2 times X1, that's the number of oxygen atoms just because of the first molecule. You can do the same for all the others. That then gives you an equation of 2x1 plus 2x2 equals, because of the right-hand side, x3 plus 2x4. You just do that now for all of them, all the atoms. There's only one left. That will then give you this particular linear system. That linear system then corresponds to that augmented matrix. At this time, I will row reduce. And I'll row reduce it to a row reduced echelon form, because it's unique. Also because there's something fun going on here, and you need to know how to interpret it. So notice that there are 3 leading entries. So there's 3 leading variables, which means there's 1 free variable. So there should be an infinite number of answers. That's what you expect, though, because if the equation is balanced, then you can take that equation that's balanced and multiply by any, well, non-negative integer all the way through, and you get an equation that's, well, also balanced. So there's automatically an infinite number of answers once we have one non-trivial one. So we're going to go look for the simplest integer solution. That means we want x1, x2, x3, x4 all be integers, and we want no common factors between them. So to do that, here's how to write down the solution like we normally do. But then notice how there's a fraction multiplied to t in a number of these equations, and all of them have a common denominator of at least 14. So I'm going to, in x4, which is right now t, I'll call t and assign it to be 14s. By making that substitution everywhere else, you then get a different representation for x1, x2, x3, and x4 in the parameter of s instead. Now, many times students will say, but they're different answers. No, because t and s can stand for any real number. So this actually generates the exact same solution sets. It's just a different way of saying them. Don't forget, when you think of it in terms of direction vectors on lines, because this is actually a line in like 4-dimension space. If you have a direction vector, any multiple of it is also fine. It still describes the direction of that line. So same idea. So if I just use s equals 1, I then get the following balanced equation where all the coefficients are integers and there's nothing in common between all of the integers. And I think that's it for that example.